Okay, so let's look at page 30 in our notes. And what we want to be able to do is use the definition of continuous to find the value of k such that this is continuous. So what I do is if I look here, these are both polynomials. This is a quadratic, this is a line. So I know those are continuous everywhere. So I don't have to worry there. The part that I have to worry about is at 2, because I got to make sure these quote-unquote hook up, like that is no longer a good math term anymore. But when I say that they're at the exact same spot. So as long as the limit of g of x as I head towards 2 from the left equals the limit of g of x as I head towards 2 from the right, then I know that this will be continuous at that point. Okay, so let's go ahead and let's do that. Let me grab my notes here. So I'm going to say that the limit of g of x as x approaches 2 from the left is going to be equal to 4k. Now, why do I know it's 4k? Because I'm going to plug in that 2 right there. 2 squared is 4, so it equals 4k. Okay, the limit as x approaches 2 from the right of g of x equals. So notice I'm doing direct substitution. That's why I can say equals. So if I plug 2 in here, I have 2k minus 6. Now, if these two things are, if it's continuous at that point, then these would have to be equal to each other. So that tells me that 4k has to equal 2k minus 6. So let's see. So 2k equals negative 6, and k would have to equal negative 3. Okay, so let's double check, and let's prove that it's continuous. Okay, so the limit as x approaches 2 from the left, if k is negative 3, then, okay, let's just go ahead and let's put it in, is negative 3 times 2 squared, which would be negative 12. The limit as x approaches 2 from the right, so k we said was negative 3, so negative 3 times 2 minus 6, so that's going to also be negative 12. So we know that the limit as x approaches 2 exists and is equal to 12. So I'm going to say, and then let's also find g of 2. So g of 2, I got to use the top function. So k, which is negative 3, times 2 squared is negative 12. Okay, so since the limit as x approaches 2 of g of x equals g of 2, and I can say, if I had a little more room, equals 12. So I'm showing they're both equal to 12. That's a nice, easy way to get that in ahead of time. The function is continuous. And I'll say when k equals negative 3. Okay? Okay, so let's look at this one right here. So this is kind of that weird one. I'm going to make a little graph for that. So I know that we saw this graph before, and 1, 2, 3, 4, that if I go, like if I put a 5 in here, 5 minus 4 is 1, it'd be 1 over 1. I'm going to get 1 going this way, and then going this way, I'm going to get negative 1. And again, go back in your notes if you forgot that. Okay, so we want this thing to be continuous. Well, I know that this is continuous everywhere except for 4. And I know that this is a line. That should be continuous. So 4 is the issue that I want. Okay, so let's see. The limit as x approaches 4 from the left of h of x. That is this one right here. So as I'm coming from the left, it equals -1. Okay, the limit as x approaches 4 from the right of h of x is 5k minus 16, because I'm going to take that 4 and I'm going to plug it right in there. Okay, so if these two are continuous, then these have to equal each other. So I know that -1 is going to be equal to 5k minus 16. So let's see, what does that tell me? 5k equals 15 and k equals 3. Okay, so now let's prove it. Okay, so the limit as x approaches 4 of h of x equals 1. So I'm kind of just showing you like different ways, because you kind of already proved it left and right. So you could just say, I know that. And let's see, what is h of 4? So if k is 3, this is 15 minus 16, which equals -1. Whoops, this was -1. I'm sorry. Okay, so thus the function is continuous. I'm not even going to write that all down, because it would be like this, that you would make a conclusion and all that good stuff. Okay, so let's look at this third one here that says, okay, for what value of x is this not continuous? Well, I know it's continuous on each piece. Okay, so let me just kind of make a note that it's continuous on each piece. And I know that because they're all polynomials. And we talked about that in our last video. Okay, so the only place that there could be a problem is we're going to investigate what's happening at -2. Are all these pieces hooking up at -2? Now, if I wanted, I could sketch a little graph of this thing. And I would see that, okay, if this was -2, that if I'm less than -2, that's the graph of a line. And it's going to look kind of something like that. Okay, I'm just getting a little sketch of what this looks like. It tells me when x is -2 that y is 3. So something like that. And when x is greater than -2, it's some cubic function. And I'm going to check out. At -2, that'd be -8 plus 12 is 4. 4 plus 3 is 7. So it's way up here somewhere. Okay, so I don't even know what it looks like. But this is just kind of giving me a general idea that this thing is not continuous. So it's kind of nice to know where I'm going, but I have to prove it. Okay, so let's justify. Okay, first thing, let's do the limit as x approaches -2 from the limit, or from the left. Okay, as we're coming from the left, we're down here. So that's equal to -2 times -2 minus 5. So that's 4 minus 5. That's equal to -1. Right? Check my work there. Okay, the limit as x approaches 2 from the right, -2 from the right. Okay, that is this. So that's -2 cubed minus 6 times -2 plus 3. So -8 plus 12 plus 3 is 7. Okay, so that tells me that the limit as x approaches -2 of h of x does not exist. Oops, sorry. Okay, and then let's even do the third step, or the second step. What is h of negative 2? That's equal to 3. Okay, so the limit doesn't exist. It doesn't equal that. So I'm going to write a conclusion, which would be like step 3, that the limit, or I guess I should put step 3 over here. I'm going to say the limit as x approaches negative 2 of h of x does not equal h of negative 2. So the conclusion, h of x is not continuous at x equals negative 2. Whew. Okay, there it is in a nutshell.